Hi, everyone. I'm Alex Krentsel from UC Berkeley and Google. And in this talk, I'm going to tell you about an increasingly important class of network outage root cause that we think hasn't received much attention for the past 15 years. So if we look at the state of SDN WANs today, we see that outages just continue to happen, despite approaching decades of experience and a variety of techniques reported by the research community meant to catch and prevent them. And anecdotally, we see this to be true across network providers, including Azure, Amazon, Meta, Google, and others. In our previous work appearing earlier this year in 2024 at SIGCOMM on decentralizing the SDN control plane, we noticed this pattern and talked about an architectural simplification to try to make these outages happen less frequently. Today, I'll talk about what we found taking a closer look at these outages and their root causes. So, why do these outages continue? To understand this, let's first take a look at what SDN WAN architectures look like today. So in these networks, there is an SDN controller that sits at the top and makes decisions about what should happen in the network. There is control infrastructure that collects relevant low-level signals, both directly from within the network, such as interface status from the routers, and from outside the network, such as host-reported sending rates, which it aggregates into an abstract view of the network that it provides to the controller. The SDN controller then uses this view in calculating new paths and behaviors from the network, which it then programs back into the routers through that same control infrastructure. Now, to understand the source of outages, we conducted a root cause analysis of high-impact SDN WAN outages over the past 5 years at Google, and found, perhaps surprisingly, that over a third of these large outages were root caused to incorrect inputs provided to the controller. And based on looking at other outage reports, we believe this to be the case across SDN WAN providers. Now, this definition of incorrect inputs is subtle, but very important. Incorrect inputs are ones that do not reflect the reality of what is truly happening in the network, such as reporting links that are down to be up or vice versa, missing or overstated demand, etc. That is, they are spurious, but not invalid or obviously wrong by their syntax. Now you might ask, how is it possible for these inputs to be wrong if we're reading our state directly from the routers? The answer lies in the complexity of the control system. So despite this conceptually simple diagram, in reality, the reality is much more complex. So the control infrastructure here spans millions of lines of code over a complex logical and geographic hierarchy of services. The router operating systems themselves and their telemetry clients are hundreds of thousands of lines of code with rolling updates to add feature support. External inputs are read from hosts, system configuration, etc. And the entire system is constantly in flux as links and routers are brought up and taken down for maintenance. So as a result, bugs can happen anywhere in this system. So in the telemetry provided to routers, by routers, in the external inputs, in the aggregation and control infrastructure, etc., that results in the produced inputs, the very top of this control infrastructure, being wrong. To illustrate what some of these outages look like, I'll tell you about a few real-world examples that we've seen. So in one outage, a bug introduced to the smoothing logic in the demand instrumentation service led to demand being under-collected and under-reported. So a partial demand was fed to the SDN controller that resulted in paths that were under-provisioned, which resulted in severe congestion. In another outage, a race condition introduced to the topology instrumentation service caused it to aggregate the topology before all routers finished providing their link statuses, which again resulted in a partial topology fed to the controller, and again, paths that were under-provisioned, missing capacity. In a third outage, an automatic drain signal that was overly sensitive was incorrectly triggered, draining a significant number of perfectly fine routers that could have just been carrying traffic, which again took down a decent amount of capacity. And in yet another smaller outage, a vendor bug caused reported telemetry values to oscillate between 0 and their actual value, which triggered a link flat protection system in the control plane to incorrectly drain affected links. Now, you might also ask, why is this not caught today? Well, engineering teams know that their systems may receive incorrect inputs, and so they do check for outliers or anomalies, such as topology missing more than half of its expected routers, or an empty demand matrix. But this misses the crucial underlying issue that incorrect inputs are often possible values, but not actually current values. That is, a topology reported missing 15% of its routers may actually be a case of widespread router crashes, or it may be an incorrect input due to a bug in the control infrastructure. There's no way to tell from that input alone. So therefore, we believe that this problem requires an alternative approach to the static checks in use today. To derive this approach, let's go back to our goal, which is to validate that the abstract inputs given to the SDN controller agree with reality. But what exactly is reality in this picture? Well, we observe here that really truth or reality is what's happening at the routers themselves. And we actually have many signals available from the routers about what's happening, beyond just the low-level signals taken by the control infrastructure today to construct the inputs themselves. These signals include interface byte counters, packet drop counters, forwarding entries, different types of probes, etc. And so we can use all of these signals together to get a more complete picture of reality. But as we mentioned before, everything here is complex, including the telemetry clients themselves. And we saw many instances, including the one I mentioned earlier, and we mentioned more in the paper, of small outages related to buggy telemetry. So how do we know that we can trust all of these low-level signals to use in our validation? Well, what we have going for us is that because of the way a network is interconnected, network actions affect or are reflected in multiple measurements. So for example, a packet being sent through the network is reflected in incremented interface counters at each router and on each side of each link, which kind of introduces some amount of overlap or redundancy into our set of measurements. So if we look at all of our measurements together, they ought to make sense or be congruent in some way. Thus, the intuition behind our approach will be to use this redundancy inherent to network data to check that the reported network state agrees with itself, and maybe even self-repair offending measurements. So more concretely, in order to do this, we will collect all known signals, both those taken by the control infrastructure today, but also additional signals available from the routers, and then attempt to refine them into some self-consistent, trustworthy state through a process that we term hardening in the paper. Once we have the hardened signals, we can use them to validate the correctness of the abstract inputs by checking that certain human-defined expected relations hold between the low-level signals and the abstract inputs. And in our paper, we call these relations invariants, as they should hold for all abstract inputs that are true. These relations are specified ahead of time by a network expert, and their complexity varies based on the input type. And we discuss them in more detail in the paper, but I'll walk through one such set of invariants that we identified in detail in the next few slides. But in this paper, we present our system HODOR that performs such validation continuously, ingesting network measurements and applying validation checks on the controller inputs. So after collecting all signals, HODOR begins by hardening the network snapshot. There are many examples of the kind of redundancy that we seek to take advantage of. For example, there is link symmetry, which says that packets sent on one side of a link or placed on one interface should match the packets received on the other side of a link. Another is flow conservation that, simply put, says that packets shouldn't ever disappear at a router. Or mathematically put, that the sum of packets or bytes received at a router should equal the sum of packets sent plus the sum of packets dropped. There's also redundancy available through alternative signal substitutions. So that is, some observations, such as an interface being up or down, must coexist with other observations, such as 0 bytes being sent or received. Another thought we had in the paper was that we could also manufacture redundancy when there's not enough naturally available through taking explicit additional actions such as sending a probe to confirm that an interface is up or down. And potentially many more. We don't claim this to be an exhaustive list. Rather, it's an illustrative set of examples of what we mean by redundancy. But it's this kind of redundancy that we can use to detect and correct inconsistencies in our low-level signals. So, for example, for a two-node topology like this one, first, via expected link symmetry, we can detect that there's some inconsistency in the reported counters in the snapshot, specifically the ones highlighted in red from A to B and received from at B from A. Then, via flow conservation, we can see which router is self-consistent in the values it reports and which isn't. And thus, taken together, these two forms of redundancy allow us to rederive the correct value for the byte flow on this link. Then, with hardened signals in hand, Hodor can continue on to doing actual input validation, checking for expected relationships to hold between these hardened signals and the abstract inputs. So let's consider specifically the case of demand, which is a high-level input to the SDN controller, referring to end-to-end flow counts, regardless of the path taken. In the case of Google, it actually comes from instrumentation directly on the hosts. Well, we observe that it must be the case that the sum of the demands reported from all nodes to a particular router must be equal to the egress interface counter at that router. This kind of relationship holds for all ingress and egress routers, mapping to the rows and columns of D, providing us two-end validation checks. If all of these checks hold, the input is validated. And if some fail, the input is suspected to be buggy. I'll note that in general, this step is challenging. Some high-level inputs we can validate trivially by rederiving portions of the input from the low-level signals and comparing. But for others, such as demand, the set of invariant checks is more complex and may not be high-dimensional enough to rederive the inputs themselves, but rather can give an independent binary indication of correctness with some confidence. It's an open question we talk about in the paper, to what degree each input can or can't be validated from available router level signals. But as a system, Hodor verifies that such relations continue to hold for each given input and the associated trusted snapshots. Now, in the paper and in our ongoing work, we raise a number of questions and that we're continuing to look into. First is how we go about building this system in the face of real-world challenges, namely the noise in the data introduced by collection time skew, but also availability requirements for kind of anything that's related to a control system for a network. We present some simple techniques for tackling this in the paper, but in general, it remains an open question. We also consider alternative approaches in the unsupervised learning space, such as masked autoencoders and symbolic regression, which can enforce or learn invariance and better account for time skew noise in the data, but come with some drawbacks that are discussed in the paper. We consider the correct space of response actions for a validation system, whether to fix an input if a fix is readily available, fail static, page an SRE, or just continue, which at the end of the day really is up to operator policy. And finally, we wonder how prevalent incorrect inputs are in other network control systems. Anecdotally, we've heard of similar issues for cloud tenant networks and data center networks, and we're wondering to what extent our techniques may enable us to help there. Now, much work remains to build this out into a real-world system, but we hope to engage here with the rest of the networking community on this important new class of outage in the pursuit of ever more reliable network infrastructure. With that, thank you, and you can find the paper here at the QR code shown on the screen, and please don't hesitate to reach out to me at this email if you're interested in this work or want to discuss further. Thanks.